So I had a couple of requests from you guys to go back to doing our summary pages like we did when we met face to face. And I think that's a really good idea, particularly for the next series of topics. As mentioned, we're going to be talking about confidence intervals and hypothesis tests repeatedly, but just in different settings. So let's review the big picture for confidence intervals and hypothesis tests for one proportion. And I think this will really set the stage for the next topic of confidence intervals and hypothesis tests for two proportions. So remember, we're in this idea of statistical inference, where we are using data we've collected to make a prediction, an inference, an estimation about the entire population. So first procedure we looked at was confidence intervals. So on our summary page, you can label this confidence intervals for one proportion. Notice I'm using the symbol here in parentheses P to remind us our goal is to estimate the population proportion. That's what P stands for. So that's our target. We don't actually have the entire population at hand, but we're going to use our data to estimate this population proportion with an interval that has some level of confidence. So I mentioned every confidence interval has the same three pieces. Starts off with our point estimate. So in general, every confidence interval is going to have our point estimate based on the data. Here's my estimate. So if we're talking about a confidence interval for P, the population proportion, then my data is P hat, the proportion from the sample. We know this will change from sample to sample, so we're going to add and subtract this margin of error. And our margin of error always has two components here. One is our multiplier, which gives us our level of confidence. So in the case of the proportion, our multiplier we called previously Z star. We saw that comes from a normal distribution. If you want to write a little reminder to yourself, we use inverse norm on our calculator to get that. Go back and look at previous notes if you have forgotten how to do that. And then the second part of our margin of error contains the standard error, how much we expect our point estimate to vary from sample to sample. When we're talking about proportions, our standard error was that P hat 1 minus P hat over N, all under the same square root. So again, every confidence interval, estimate from the data, plus or minus margin of error that has a part for confidence and a part for variability of your data or statistic. Once we come up with this, it's very important to be able to interpret your interval as well. So the interpretation, we need to see three parts of this. The first one is how confident you are. So I'm going to throw 95% confident in here, but that could be different depending on the problem. So that's the first thing. How confident are you? If you want to use more formal language, again, you could say something like this study is whatever percent confident. The next piece is what you're trying to estimate. Remember up here, we're trying to estimate P, the proportion for the entire population. So we're 95% confident. The proportion of all, or the true proportion, the population proportion, say that somehow, and then give it some context. I'm just going to put ellipses here. So, proportion of all people in the U.S. that smoke, or whatever the context is. We're 95% confident the proportion of all blah, blah, blah. And then the last part, give your interval, is between blank and blank. Okay? Never use the word data in this interpretation. The data, we're 100% confident and smack dab in the middle of our interval every single time. All right, so that's a confidence interval. The other procedure for inference we were talking about is hypothesis testing. We mentioned the duality, that these guys are always going to agree. When we do hypothesis tests, we're looking for all 5 steps. If the problem doesn't spell them out for you, it's still expected that you do all 5 steps. So first step, state the hypotheses. So we have always 2 of these guys, our null and our alternative. And just as a reminder, the alternative is where our research claim goes. And HO is our initial assumption, what we start off assuming when we do all our calculations. When we're talking about proportions, the notation is going to look like this. Our research question goes in HA. We're going to use P to say we're asking a question or making a claim about the population proportion. Do not use P hat. We want to make a claim about everybody, not the data. And our options are that proportion is smaller than, larger than, or somehow just different than our initial assumption. So this P naught is coming from our claim, our research question is not coming from the data. And H naught, where we get that notation, is that P, the population proportion, is equal to that value. So we start off assuming it's that number from our claim, and then we try and test or see if we can prove if it's different according to our research question, less than, greater than, or not equal to. All right, once we started off, we've stated what we're going to assume and what we're hoping to prove. Now we go collect our data, our evidence here, and our evidence is our data, and remember that's just P hat. What's the proportion in the data that we've actually observed? So in general, this test statistic is going to look sort of like a z-score. It's going to be our point estimate, or the data we've observed. We're going to see how far that is from our initial claim. So point estimate is our data, our evidence. How far is it from the null hypothesis, or that initial claim, over our standard error? So we said that looks like a z-score. Let's check out what that means in the context of proportions, specifically one proportion. Our point estimate, if we're talking about proportion, is P hat. There's the data, the proportion of the data that I've observed, minus the null hypothesis is P naught. That's what I'm assuming the proportion is. So I'm seeing how far is my evidence from that initial assumption. And then I'm going to divide by our standard error, the expected variability. So we've seen this a few times already. And as a reminder or emphasis, the version of P we're using down here is the one that goes with our null hypothesis. We're standardizing, subtracting mean, standard deviation, according to HO, that initial assumption. All right, then next bit, we need to calculate our p-value. Write a reminder to yourself, P is for probability, needs to be between 0 and 1. If you're not getting between 0 and 1, you're messing something up here, making a mistake some way. It's a probability, so your answer needs to be between 0 and 1. And specifically, it's telling us what are the chances of seeing our data, or more extreme, under this assumption of P naught. That's what we're plugging in here. Okay, so we also said it depends on HA. For what we mean by our more extreme part of this calculation. So we had 3 different versions for HA, if you remember. Our research claim could be less than, greater than, or not equal to. So we need to consider each of those cases. So we had if HA was less than was one option. Our picture looked like this. Our test statistic or evidence, we rescaled it in the form of a z-score. So maybe this is my test statistic I've calculated. Since HA is less than, my p-value is going to be the area less than my test statistic. And we've done this a few times. There's our normal CDF. My lower is going to be negative infinity up to your test statistic. Our other option, what if HA was greater than? So I'm just going to draw the same z-calc on all of these. Again, the second case, HA is greater than. Then that means I need to shade everything above my test statistic. The or more extreme means greater than. So we'll do normal CDF. My lower this time is my test statistic out to infinity, everything greater than it or above it. And then our last option was HA not equal to. So this one was our two-sided test where we had either option as a possibility. What are the chances of being that far away from my assumption, either less than my test statistic? And I'm just going to use this notation to say check out the negative version of your test statistic, that negative discrepancy between data and initial claim, and positive version. So our p-value is two-sided here, comes from both tails. And we said you had options. Find one of these sides, and because it's a mirror image around 0, just find one of them and double it. So I could do normal CDF and the lower tail, negative infinity to the negative version of my test statistic, and just double that to get both sides. Or I could find the upper tail and double that. So the upper tail is going to be my test statistic here out to positive infinity. So positive version out to positive infinity to find this bit, and then don't forget to double it. So if HA is not equal to, you need to find one side and double it. Less than or greater than, it's talking about one specific tail, one specific direction. No doubling needed, just find that one specific direction. All right, almost done. Once we find the p-value, make sure you can explain what that means. A lot of people use p-values in practice and have no idea what they mean. So interpreting this, the first thing we're going to look for is a statement about the assumption if the null is true. I'm going to write that reminder out here. So the reason is, check out our test statistic. We assume the null was true. We defined in our hypotheses. H naught is our initial assumption. So H naught is that p is equal to some number. We plug that number in here and we're measuring how far is our data from that assumption. So let's put that in our wording here. If H naught is true, okay, so let me underline that. You would put that in context depending on your problem. What does it mean for the null to be true? The proportion is whatever value. We would see data like ours or more extreme. Okay, again, this comes from how are we finding this probability? We're checking out our data, that z-calc is our data compared to the null, or more extreme, we're shading from our data or more extreme, and that or more extreme again is defined by our HA. We'd see our data or more extreme, p-value times 100% of the time. So here, when you find p-value, that's as a decimal, multiply by 100 to make it a percentage in your interpretation. Okay. Then the last part, our conclusion, is going back full circle and should be in terms of HA, your research question. So our conclusion depends on our p-value and what we just said here. So if the null is true and we have really low chances of seeing our data, that probably means the null is not true and instead our research question is. Let me say that again. If the null is true and we have really low chances, we get a really small p-value of seeing our evidence, the evidence doesn't support the null. The null is probably not true and we have good evidence for our research question or HA. So here, your wording, again, always in terms of HA, it should be something like this. There is some kind of evidence for HA, and again, HA, put your research question in context of the problem. How much or how little evidence you have for your research question depends on your p-value. And we gave some guidelines in the notes. Let's add them here as a reminder. So our guideline for that wording, we had the general idea, the smaller the p-value, the stronger the evidence you have. So if we have a p-value that's really small, less than 0.01, So you see data like ours are more extreme less than 1% of the time under the null, then we have really good strong evidence. So very strong evidence. Put that here for the research claim. If our p-value is smallish, so somewhere between 5% and 1%, then we've got strong evidence for the research question, a research claim. And then maybe we have a p-value somewhere between 5 and 10%. So still not likely, but not as rare as the last category. We might say we have some evidence for HA. And then finally, if we have a p-value that's pretty large, anything over 10%, that's like saying if the null's true, we have more than a 10% chance of seeing our data. We're going to say that's rare enough, or that's often enough, that we can't rule out the null, and we don't have any evidence for our research claim. So I'll say little to no evidence for HA. All right, the next video we're going to translate all this stuff into two proportions, and you'll see that a good foundation here will make transferring the knowledge to two proportions a whole lot easier.